Vectors are very important for both physics and mathematics. Vectors are things that have both a size, sometimes it's called magnitude, as well as a direction. Force, for example, in physics would be represented by a vector. What that means is I can push in that direction, or I can push in that direction, and I can push hard or I can push softly. Similarly, velocity is a vector. I could be going very fast in that direction or in that direction, or I could be going slow in those directions. Compare this with the concept of a scalar. A scalar doesn't have a direction. For example, mass. Knowing the mass, one certainly can tell that one man is skinny and the other is fat, but we cannot say where either of them is going. There is no information about direction. Similarly, if you know the temperature, all you know is that one body is cold and the other body is hot. Again, no direction. On the other hand, a vector has both size and direction. That size is sometimes called length, sometimes called magnitude, and also the norm. So if we look at this vector, it's pointing in a certain direction. This vector is pointing in the same direction, but it has about half that length. On the other hand, this vector and this vector have the same magnitude or the same length, but they are pointing in different directions. Here's a physical example. Here's a man who's pushing a trolley with a certain force. Let's call that F. So this is the force vector. If he pushes twice as hard, that vector will be twice as long, but again in the same direction. On the other hand, suppose you have this situation where this man is pulling towards the right and this man is pulling towards the left. If they pull with the same force, that is to say the vectors are equal and opposite, then neither of them will make the rope move. There's a very important property that we give to vectors. Suppose that this is a vector of a certain length in a certain direction. We'll call this the tail of the vector, and we'll call this the head of the vector or the tip of the vector. Now, if we move the tail and the head such that the tail comes here and the head comes here, but in such a way that the length does not change and the direction does not change, then we say that these two vectors are exactly the same. Let me illustrate the idea of parallel transport by taking this example of an aircraft that's flying over Islamabad at a constant speed of 250 kilometers per hour. Its direction is given by this vector over here. We'll call that the velocity vector. When it's diving, the speed increases to 300 kilometers per hour and the velocity vector points downwards. When it's climbing, the speed decreases to 150 kilometers per hour and the velocity vector points upwards. Now imagine an identical aircraft that's flying over Lahore. And again, when it's in level flight, the same speed and the same direction. We're going to require that this velocity vector be exactly the same as this velocity vector, and this velocity vector be the same as this velocity vector, and that this and this be also the same. So these vectors, although they have different tips and tails, are nevertheless exactly the same. We'll now put various requirements upon a vector. To begin with, if we multiply it by a scalar, then that vector should remain a vector. So for example, if we multiply the vector A by 2, then it becomes the vector 2A. This is a vector that's pointing in the same direction but is twice as long. In general, if we have the vector A and we multiply it by, let's say, a number A, then A times A will be a vector, again in the same direction, but which is A times as big. What if A is minus 1? Then we have a vector that's pointing in the opposite direction. So minus A is a vector which has the same length but the opposite direction. And now this then brings us to the question of what if there is both A and minus A and we add them together. Think of it in the following way. There's someone pushing in this direction and there's somebody pushing in the opposite direction. What should be the net result? 0. And so we're going to demand that A plus minus A be equal to 0. But there's one thing to be careful about. This 0 is not the number 0. This number 0 is the vector 0. The vector 0 has got 0 length, and it's pointless to talk about its direction, of course. We saw that A when added to minus A gives the 0 vector, but what happens if A is added to another vector? Let's call it B. I'm going to use a nice animation that's developed by David Harrison, referenced over here. At the first step, A is parallel transported, and then B is parallel transported. Then we join the tail of A to the tip of B, and that gives another vector, which is the vector sum of A and B. But then you could ask, what happens if we do it in the other order? In other words, first parallel transport B, then parallel transport A, and then join the tail of B to the tip of A. Let's call that C2. So the vector C2 is the sum of B and A, or you could call it the vector sum. Are C1 and C2 the same? Well, let's parallel transport them. And yes, they are exactly the same. So it does not matter whether you add A to B or B to A. That is called the commutative property here, the commutative property of vector addition. Using the idea of vector addition that we just saw, let's see how to subtract two vectors from each other. So here are two vectors. Here's A and here's B. What we want to now calculate is A minus B. Well, that's easily done. Parallel transport A, parallel transport B, but turn it around. Minus B points in the opposite direction. And so now you have a triangle. Here's A, here's the vector minus B, and their resultant is C. C is A minus B, which is the same thing as adding A to minus B. There's another way that you could look at this. It's completely equivalent. So parallel transport C, parallel transport B, parallel transport A. And in this triangle, you see that C plus B is equal to A. You see that it also makes algebraic sense, because if C is equal to A minus B, then C plus B must be equal to A. We've learned the rules for adding two vectors together. What if there are three vectors that we want to add? Well, that's easily done. First, we will add two vectors together. So A added to B gives this vector here, A plus B. And now what we'll do is add C to A plus B. And this blue vector over here is the vector sum of A and B added first and then added on to C. We could have done this in another order. First, add B to C, get B plus C, which is over here. And now to this green vector, b plus c, we're going to add a. And so here we get a plus b and c added together. Compare that with a and b added together and then added on to c. Let's see if they are the same. And indeed, when parallel transported, they are exactly the same. This is the associative property that vectors have. And this is a property that we have given to vectors. We require them to obey a added on to b plus c be the same as a plus b be added on to c. Vectors that are perpendicular to each other, that is to say there's a right angle between the two vectors, and which have unit length, are very useful and they're called unit vectors. So, for example, if we take a unit vector which is in this direction and has unit length equal to 1 in other words, this is sometimes called I, and here's a vector that's perpendicular to it and it's got j with a little hat on top of it. That hat tells you that it's a unit vector. Now let's say you multiply the unit vector in the x direction, that is to say the unit vector I, by maybe 3. Then you see that there is a vector here along the x direction which has got size 3. Let me put that back. Now let me do the same thing for the unit vector in the y direction. So let me multiply it by 3 and I get to this vector over here. Now what if I multiply both j and I by 3? So you can see that I am reaching this vector which has got 3 units of length in this direction and 3 units of length in this direction. The length of c, which is the resultant vector, will be, by Pythagoras' theorem, the square root of 9 plus 9, which is square root of 18, and that's 4.24, as you can see over here. You can see that by changing the number that multiplies the unit vector I or the unit vector j, you can go to different vectors that lie in the xy plane. We've just seen that any vector in a two-dimensional plane can be written as a sum of two parts. So suppose that this is the vector A, any vector. This is the unit vector I, which is along the x direction. And this is the unit vector j, which is along the y direction. Then any vector A can be written as ax is a number, times the unit vector I plus ay times the unit vector j. And this axi is a vector which is pointing along the x direction and has length ax. And similarly, ayj is a unit vector that's pointing in the y direction and has length ay. So it is quite common to write the vector A as ax and ay. Now, I should say that a lot of people don't use I and j. They use the symbols ex, ey, or sometimes e1, e2, or sometimes even x and y. But they all have these little caps on them to show that they're unit vectors. But now, let's see what happens when we have a second vector. So here's the vector A as before, but now there's this vector B also. So if A is ax, ay, B will be bx,
by. So this could be like 2 and 1, and this could be like 3 and half, or whatever. Suppose we add up these two vectors. Well, in that case, A plus B is then, you see over here, AX times the unit vector I plus AY times the unit vector J, and that's the vector A. And similarly for the vector B, we have BX I plus BY J. And now we can just take the unit vector I common and write this as AX plus BX times I plus AY plus BY times J. Now these numbers AX, AY and BX, BY, these are called respectively the components of the vectors A and B. So what we have over here is that in adding the vectors A and B, we've added their components in this way. And so actually this is a rather simpler way of adding two vectors, but it's entirely equivalent to what we learned earlier, which was that if this is A and this is B, then you make a triangle AB, and then this becomes A plus B. Let's see why that is so. Well, that's pretty clear actually, because if this is AX, then this over here is BX, and so this total length from here to here is AX plus BX, and that's the length of this vector AX plus BX into I, and that's obviously along the X direction. And similarly, this over here is, we know this is AY, and from here to here is BY. So AY plus BY, that's exactly what we have over here. Now, these vectors I and J are very important in another sense. They're called basis vectors. Why are they called basis vectors? That's because by taking different values of AX and AY, you can get to any vector A. So these are basis vectors, and we have then a term that they span the 2D space, the two-dimensional space. In other words, if you take any combination of I and J, you get to a vector. And if you take every possible combination of AX and AY, let's say AX is equal to 1, AY is 1.342, in this way, you will get to every possible vector that can exist in the xy plane. In other words, you have then spanned the entire space. The idea of having vectors in a three-dimensional space is actually very similar to what we've just learned in 2 dimensions. So here we have a vector A, any vector. The difference from earlier is that it has a component along the z direction. And let's call, as before, our unit vectors in the x direction I, the unit vector along the y direction j, and the unit vector along the z direction k. So any vector A can be written as ax times I plus ay times j plus az times k. And we'll say now that I, j, and k span the 3D space. In fact, we could now continue this idea. We could have I, j, k, l, and then you would have a 4-dimensional space. And if you had I, J, K, L, M, N, O, P, Q, R, S, T, etc., we could go to many, many dimensions. Of course, we wouldn't be able to draw it, but the ideas would be very similar. So far, the only thing that I've said about multiplication is that if you have a vector A, then you can multiply it by a number, let's say 7, and get a vector that's 7 times longer than A. But now we're going to learn how to multiply a vector by another vector. You can do this in 2 different ways. The first is you can take what is called the dot product of 2 vectors. In this, the vector A is multiplied by the vector B to get a scalar or a number which is called A dot B. What that means is the following. Suppose I have one vector and another vector. Let's call this A and this B. And there's some angle that's between them. Call that theta. Then A dot B. And it doesn't matter whether you write A dot B or B dot A. They're both the same. That's defined to be the length of A, the length of B, times the cosine of the angle between them. And this notation is something that you'll see very often, that people write magnitude or the length of A as A. So taking this definition that we have before us, let's look at a number of consequences. First, suppose that you have 2 parallel vectors. So A is like this and B is also like this. The angle between them is 0. In that case, A dot B is AB cosine of 0, which is just A times B. So multiplying these 2 vectors together, that is to say taking the dot product, gives you just the product of their lengths. What if they are antiparallel? So let's say A is that way and B is that way. In that case, theta is pi and A dot B is AB cosine of pi, but that's minus 1, so that's minus AB. And there's another important case. Suppose A is like this and B is perpendicular to it, which means theta is pi by 2, in which case A dot B will be AB cosine of pi by 2, but that's 0, so A dot B is 0. When 2 vectors have a dot product that is 0, you say that these vectors are orthogonal. That's a word that you have to remember. Now, clearly, the unit vector I and the unit vector j, their dot product is 0. Similarly, the unit vector I with k is 0. The unit vector j with k is 0, etc. And of course, if you take the unit vector I dot product with the unit vector I, well, that's the length of I times the length of I times cosine of 0. And so this is 1. So we have confirmed that these unit vectors have got unit length. This gives us another way to take the dot product of 2 vectors. So let's say that I have a vector A and I want to take the dot product with the vector B. Well, that's AX times I plus AY times J plus AZ times K, and then the same thing but with the B's. So BXI plus BYJ plus BZK. And now, since I dot I is 1, and I dot j is 0, etc., then this is clearly ax bx plus ay by plus az bz. In other words, we just multiply the components of the vectors a and b together. This is, of course, exactly the same as this. There's a second way by which we can multiply a vector by another vector, and that's called taking the cross product. In this, we multiply the vector a by the vector b to get the vector a cross b. Now, what that means is the following. Suppose you have a vector a and this vector b, then a and b form a plane. And so that's the shaded area that's over here. The vector a cross b is perpendicular to that plane. That means that a cross b is perpendicular to both a and to b. The way in which you determine the direction of a cross b is illustrated here. This is called the right-hand rule. So if a points in this way, b in this way, then a cross b points up. If you exchange a and b, then a cross b will point down. The magnitude of a cross b is written this way. This is a times b times the sine of the angle that's between a and b. So this theta is what's over here. There are a number of different conclusions that we can make. First, if theta is 0, which means if the two vectors are parallel, then a cross b is the 0 vector. It vanishes. On the other hand, if theta is equal to pi by 2, then the magnitude of a cross b will be a into b, because sine of pi by 2 is 1. From this we can get a number of consequences. So for example, if this is the unit vector along the x direction I, and this is the unit vector along the y direction, and this is k, the unit vector along the z direction, then I cross j will have magnitude 1 times sine of pi by 2, which is 1, and so I cross j will be a vector that's along the z direction, and of course will have unit length. Now you can easily check that if you use the right hand rule, that k cross I will give you j, and j cross k will give you I. In general, and this is a very important point to note, if you have a cross b, then if you reverse the order, make it b cross a, then the sign reverses. And that's because if you're exchanging a and b, then your thumb points downwards. Now we can use what we've learned to calculate cross products in a fairly straightforward way. So suppose that a is some vector, let's say 2i plus let's say 3j, and b is another vector, let's say it's I plus let's say k. Then a cross b can be calculated in the following way. We'll just write this as from above, and now any vector crossed with itself, and there's a cross over here, any vector crossed with itself is 0. Why is that? Because a cross a is a into a, but there's sine of pi by 2. So this gives 2, well, we can just write it out since we're doing it the first time. So this is 2i cross I, but I cross I is 0. And then there's 2i cross k, I cross k, we have from here. Here there's k cross I, but we know that that's minus I cross k. And then we have 3j cross I plus 3j cross k. Now, this is 0. Then I cross k is minus j, so minus 2j. And then j cross I is minus k, so we have minus 3k. And then j cross k is I, so 3i. And so we have our answer, it's 3i minus 2j minus 3k. That's A cross B. Vectors can be very useful for proving theorems in geometry. Here we are asked to prove that for any triangle, the sum of the lengths of its two sides is bigger than the length of the third side. What that means is the following. Suppose we have a triangle, any triangle, and that its sides are A, B, and C, then, for example, that A plus B ought to be bigger than C. Now this cries out for vector addition, because if we call this the vector A, this the vector B, and this the vector C, then clearly what we have is A plus B is equal to C. And now let's take the dot product of A plus B with itself and of C with itself. So what we'll get is A plus B squared, or dotted with itself. That's the same thing. So A plus B dot A plus B is equal to C dot C. And now let's open this out. So A dot A is A squared, length of A squared. So this is now the norm or the length of the vector. And then we have similarly B dot B, which is B squared. And then we have A dot B plus B dot A, which is 2A dot B, and that's equal to C squared. In other words, from here we get A dot B is equal to half of C squared minus A squared minus B squared. On the other hand, we do recall that AB, the length of A times the length of B, always has to be bigger than A dot B, unless, of course, the two vectors are parallel, in which case they will be equal. And now that's telling us that AB has to be bigger than half C squared minus A squared minus B squared. Okay, so I'm going to take 2 on this side, and I'm going to take minus A squared and minus B squared on the other side, so the signs will change, and we'll get A squared plus B squared plus 2AB greater than C squared. From this, A plus B squared is bigger than C squared, and hence we've proved that A plus B has to be bigger than C. That's what we were after. Now let's solve this problem. We are asked to find a vector of unit length that is perpendicular to the vector 2i plus 3j. Let's call the vector that we are looking for B. And so we can write this as some number, call it alpha, times I plus beta times j. That's because I and j are basis vectors, and you can write any vector in terms of them. The first thing is that A dot B has to be 0. That's because they are perpendicular to each other. And so let's write this as 2i plus 3j unit vectors dot product with alpha I plus beta j. Now, when I take the dot product of I with I get 1, and so that's 2 alpha. But the dot product of I with j is 0, and similarly of j with I is 0, so we get nothing there. But j dot j is 1, so we get 3 beta here. And that has to be equal to 0 because a dot b is 0. And that tells us that beta is then minus 2/3 of alpha. So we are left with one unknown, either beta or alpha. But we have another equation because the vector has to have unit length. So that means that b dot b has to be 1. And so that says that alpha squared plus beta squared has to be 1. And now let me put beta from here. So that is alpha squared plus 4 over 9 alpha squared. And that's, of course, 13 over 9 alpha squared. That has to be equal to 1, which means that alpha then is either plus or minus square root of 9 over 13. Now, if we know alpha, then beta is minus 2/3 of that. So minus 2/3 of plus or minus 9 over 13. And I can take the 3 inside, that becomes a 9, which will cancel that, and this 2 will go inside, will become 4. So we get now minus or plus square root of 4 over 13. That means that there are two possibilities. So b can be either 9 over 13 square root times I minus 4 over 13 j, or we can have b as minus square root of 9 over 13 I plus square root of 4 over 13 j. So one vector points one way and the other vector points the other way. Let's make a quick sketch of both a and b. So if a is 2i plus 3j, that's going 2 units this way, 3 units this way, and this would be, let's say, a. And then b is perpendicular to that. It can be either pointing this way or this way. And you can see that in the first case, we have square root of 9 over 13 I, so that's positive x, and this is negative. So this is the first possibility, and this is the second possibility. Here's a more challenging problem. There's a plane that passes through the point P. The point P has x equal to 2, y equal to 2, z equal to 2. And the plane is perpendicular to the unit vector n, which is 1 over square root 3 I plus j plus k. We're asked to find the equation of the plane. That plane is shaded here in blue. This is the point P, and this is the unit vector n. Well, let's take the origin and the point P and join them up together like this. So we'll call this the vector A, and it has components 2, 2, 2. Now take any point on the plane that's over here. Let's call it Q, and it has coordinates x, y, and z. Now this could be anywhere on this plane. So here is the point Q, and this was the point P. The point Q has got coordinates x, y, and z. We'll make another vector which joins this with this, and that's the vector B. Now look at this vector from the point P to the point Q. The unit vector n will be perpendicular to any such vector, that is to say for any x, y, or z. Now let's make the vector that starts at P, ends at Q, and obviously this is B minus A, because if you add A to B minus A, you get B. Now let's see what B minus A is. So A is 2i plus 2j plus 2k, and B is xi plus yj plus zk. And so obviously B minus A is the difference of the two vectors, so it's x minus 2i plus y minus 2j plus z minus 2k. Now we require that this unit vector n be perpendicular to this vector b minus a, and so n dot b minus a has to be 0. Now n is given up above over here, and so this is 1 over square root of 3. And since all of these have the same components, what we get over here is x minus 2 plus y minus 2 plus z minus 2. And now we have the relation that x plus y plus z has to equal 6. So that is the equation of the plane. Let's understand why. On a plane, there are only two independent coordinates. You can go one way or you can go in the perpendicular way. You can't get off the plane. Now over here, although the coordinates of the point Q are x, y, and z, yet you can write z as a dependent variable, dependent upon x and y. Or you could write y as a dependent variable depending upon x and z. Or you could write x as 6 minus y minus z. So the point is that this is a plane because there are only two independent variables, either x or y or x or z or y or z. And so this is the equation of the plane. Now I'm going to change gears. How do you recognize a duck? Well, if it looks like a duck, if it quacks like a duck, if it swims like a duck, then it is a duck. This lecture, of course, is not about ducks, it's about vectors. How do you recognize a vector? Well, I began the lecture by saying that a vector is like an arrow. It's got a certain length and a certain direction, and from this we got a lot of properties. But now that we have those properties, we are not necessarily going to think of a vector as an arrow. Instead, we will recognize a vector by its properties. The first property is that if there's a vector A and you multiply it by a number, a scalar alpha, then you get another vector, alpha A. And so that will be the first way of recognizing something that's a vector. Next, that two vectors can be added together to get a third vector. And it doesn't matter which order you add them in, A plus B and B plus A will give you the same vector. Third, that if you multiply a vector by minus 1 and you add it to the original vector, then you'll get the zero vector. The zero vector is something that if you add to any vector, so if you take a plus 0, then it doesn't change the vector. So that's our second property. Here's our third property. And the fourth property is that you can add up three vectors in any order you like. So if you add up b plus c first and then add it to a, or add a plus b and then add it to c, then you'll get the same vector d. And you could do it in this order too. This is called the associative property. Now, we also need a way of defining the dot product. Whatever a dot b might mean, it's a number. And it's a number such that a dot b and b dot a are both scalars. By the length of a vector, we shall mean that the vector dotted into itself is the square of that vector's length. That's all that we need to recognize a vector. We don't need arrows, we don't need anything else. There are many examples of vectors that are not arrows. Let me give you just one example. So let me take a bunch of numbers, a1, a2, a3. These a1, a2, a3 can be any numbers. I'm going to call that the vector A. As a requirement, I'm going to say that when the number alpha multiplies this vector A, then I'm going to get another vector, another thing of the same type, which is alpha A1, alpha A2, alpha A3. So that's the first property that I'm going to impose upon this thing which I've called a vector. My second property is that if there's a second bunch of numbers, b1, b2, b3, and this is also to be called a vector, then the addition of a with b has to mean a1 plus b1, a2 plus b2, a3 plus b3. And so that's also, like this and this, a column of three numbers. Now, clearly with this definition, this is the same as adding b to a. It doesn't matter whether you've added a1 to b1 or b1 to a1, so therefore it doesn't matter whether it's a plus b or b plus a. As my third property, I'm going to require that if a is added on to minus a, then from here you see that I have a1 minus a1, a2 minus a2, a3 minus a3, and that is 0, 0, 0. And this over here is what I'm calling now the zero vector. It's not a number, it's a column of three zeros. Fourthly, and this I'm not really going to do, if I add a and b and I add c to this, then I should get the same as a added on to b plus c. And now that's pretty clear because you can add numbers in whichever way you like. And finally, how do I take the dot product? Now that is something that we've got to figure out. What does this mean? Because we don't have arrows anymore, we cannot talk of the angle between this column and something else. That would be meaningless. And so this thing is going to mean the following. A dot B will mean that instead of a column, I have a row of numbers. So this will mean A1, A2, A3, and B will be then B1, B2, B3. And the rule is that A1 will multiply B1, A2 will multiply B2, A3 will multiply B3, and this is then A1 B1 plus A2 B2 plus A3 B3. That is the dot product of the vector A with the vector B. But then we've got to have B dot A and A dot B being exactly the same. And so if I look at B dot A, then that is defined as being B1, B2, B3. So I take the numbers, and instead of putting them into a column, I'll put them into a row. And here I have A1, A2, A3. But it will mean the same thing, B1 into A1, B2 into A2, B3 into A3. And so we have this thing here. But of course, it doesn't matter whether you multiply numbers in one order or the other order. In other words, they commute. And so this and this will be the same. What I've shown now is that if we take our vectors to be actually columns of numbers, and if we define our inner product or our dot product in this way, then in fact we are dealing with vectors, and those vectors are not arrows.
We studied many things about vectors in 2 dimensions and 3 dimensions. And there are some general ideas that should have made themselves clear by now. The most important thing was not the cross product in 3 dimensions. Rather, it was in either 2 dimensions or 3 dimensions, if you add 2 vectors together, you get a third vector. If you add the negative of a vector to itself, you get the zero vector, meaning something that has zero magnitude. And if you add 2 vectors together, either in the first order, A plus B and then C, or you add A to B plus C, you get the same answer, and so forth. These are ideas that can be generalized very, very far. And in fact, they make up a very rich field of mathematics called linear algebra, but that's not what we're going to get into. We've learned enough for an introduction to vectors.